Alrighty, lads and ladies, welcome back to Calc 1. Today we are charging ahead, learning how to take more and more and more derivatives. Hopefully you've been practicing in the homework and are feeling somewhat comfortable. So today we will get, I think it's appropriate to do a little more practice, but the big reveal today is the trig stuff. So I want to start with just a couple product and quotient rule problems. I'll take them out of the homework. You got plenty of shit to practice in there. I don't see any harm in doing one or two of those with you, for you, whatever. But then the majority of the day today is going to be about cooking up the derivatives of the 6 trig functions: sine, cosine, secant, tangent, cosecant, and cotangent. Without further ado, here we go. So this, of course, is MAC2311, section number 004, which is Calc 1. And the date today is the 28th of January, 2022. Today, a little more practice with the differentiation rules. Right, the derivatives of exponentials, power functions, products, quotients thereof. So more 3.1, 3.2 stuff. We're going to be using these so very much all through the semester that it really is important you get very, very comfy with them. And to that end, I think a little more practice is appropriate. But the main point of the day is derivatives of sine x and cosine x, from which we will get derivatives of secant x, tangent x, and so on. Those 4 I will calculate for you explicitly today. Cosecant and cotangent, I will be giving you the results and then leaving as exercises. They are straightforward applications of the derivatives of sines and cosines with the quotient rule. So I will do these 4 for you explicitly in class. The first 2 are going to take a lot of work. And then once we have sine and cosine, getting the derivatives of secant and tangent are actually very, very easy applications of the quotient rule. So I want to start again with just a little bit of product and quotient rule practice. Let's do that. Here we go. And I'll just grab 1 or 2 little problems out here. Let's make them fun ones. See, now we did something like that the other day. F prime and F double prime, tangent line, normal line. We did one of those. This is a fun one. Yeah, and then I wanted to do one that was a little bit more on the abstract side. So let me begin with the Witch of Maria Agnesi. That curve is an important curve. We're going to find the tangent line to the curve y equals the Witch of Maria Agnesi. That's not the serpentine. That's 1 over 1 plus x squared at the point, what did they say? 2? It's supposed to, no, 1, 1/2. 1 comma 1/2. Real quick, what does that curve look like? It's graphed for you in the problem, but absent the tangent line, this graph looks like this. Kind of has a bell curvy shape. Now, when people talk about the bell curve, like in the sense of probability distributions, IQ distributions, stuff like that, they're talking about something else, not this, but it's similar in shape. This is actually the derivative of a certain important trig function, derivative of an inverse trig function. I won't spoil it for you, but you might be able to put it together by thinking about the shape of this graph. All right, so that's the curve, y equals 1 over 1 plus x squared. And if I want to find the tangent line to this thing, then as always, I need a point and a slope. So my point is 1 comma 1/2. So the tangent I'm looking for is something like this. They told us the point. The slope is the derivative of this function evaluated at x equals 1, right? So tan we know is f primed of 1, where f of x is the function from which this curve is coming, 1 over 1 plus x squared. So I'm going to need to cook up the derivative of that function. I'm going to do so using the quotient rule, not the limit definition, because now that we know the product quotient rules, we can use them freely. And then I will plug 1 into that derivative. Let's do it. I'll remind you really quick what the quotient rule says. Some people like to write these in terms of the variables u and v rather than f and g, because so often we use f to describe the function we're working with, it can be a little bit confusing. So let me go ahead and give you that. Again, the way I remember it is that little mnemonic, low d high minus high d low. So that's the bottom times the derivative of the top, low d high, minus high d low, u times v prime, over the bottom squared, low low. So low d high, bottom times the derivative of the top, minus high d low, top times the derivative of the bottom, all over the bottom squared. That's the main tool here. So the derivative of 1 over 1 plus x squared, and again, I strongly encourage you to write these out kind of schematically. That's the bottom times the derivative of the top, so 1 plus x squared times the derivative of the constant function 1 minus the top 1 times the derivative of the bottom 1 plus x squared all primed, divided by the bottom squared 1 plus x squared all squared. So taking the time to write it out like this before you do the actual calculation makes the chance of success much greater, because the chance of a silly mistake is much smaller. I like to say, let the page do some of the work for you. Let the page remember the context. You just worry about the individual calculations. By writing it down, you get it out of your brain on the page, where the page will do the memory part for you. 1 primed is 0, right? The derivative of the constant function 1 is 0. So this is 1 plus x squared times 0 minus 1 times the derivative of 1 plus x squared. That's 1 times derivative of 1 plus x squared is 0 plus 2x, or just 2x. And all of this is divided by 1 plus x squared quantity squared. I would just leave that like that. There's no reason to FOIL that out. Certainly not at this stage, but I can simplify a little bit. This piece times 0 goes away. Minus 1 times 2x, that's negative 2x. So altogether, we have just negative 2x divided by 1 plus x squared all squared, like this. So here's the derivative of 1 over 1 plus x squared. Thus the slope of my tangent line should be f primed of 1 is this derivative, but with the number 1 plugged in for x. So that's negative 2 times 1 over 1 plus 1 squared squared. The numerator is negative 2. The denominator, 1 squared is 1, 1 plus 1 is 2, 2 squared is 4. So this is negative 1/2. And now you've got your point, you've got your slope. Therefore, your tangent line is y minus the y value at that point equals your slope negative 1/2 times x minus your x value at that point. That's the tangent. Not bad. Not bad at all.
Wouldn't it be y minus or y plus 1/2?
No, the point slope formula, remember, is y minus y0 equals m times x minus.
Oh, you're right. Sorry.
That's all right.
I also had another question. When you were taking the derivative, and the one, like the 1 prime, it became a 0. Is that because like constants become 0 when
Yes,
you take the derivative?
Yeah,
Okay.
that's exactly correct. The derivative of any constant is 0. Yep. That's also why this was just a 2x. The 1 differentiates to 0, so we get 0 plus 2x. We can think of that as a separate rule if we want. Derivative of constant is always 0. I think in a sense, it's nice to have that awareness. Or you can think of it as a consequence of the power rule, because if you differentiate x to the 0, you would get 0x to the negative 1, and that 0 makes everything 0. But either way is fine. I think most folks prefer to just remember that, yeah, derivative of a constant is always going to be 0. This is good. Any other thoughts or questions on this one? Alrighty. I promised to do a slightly more abstract problem Wednesday, and we weren't able to get to it. So let's take a look at one of those. There are two in here that kind of come to mind as problems that are a little bit conceptually challenging. One of them is like 27 or 28. 26 is also interesting. All of these where you're not given a concrete function, you're asked to come up with stuff with limited information. I think of all of these, probably 28 is the most challenging to folks. I don't want to spoil the good stuff for you though. Fuck it, let's do it. All right. So rather than copying down this whole graph, let me play it like this. So the function u is f times g. And the function v is f over g. And we want to find u primed of 1 and v primed of 5. And the graphs of f and g are given. All right, and they're piecewise linear. So let me just shrink this out of the way a little bit. Graphs of f and g are given. In order to cook up u primed of 1, I need to find a formula for the derivative of u primed of x, and then plug the bits into that formula from the graph. So first, u primed of x, I can differentiate u symbolically. Again, thinking like writing things out in that prime notation. This is the derivative of f of x times g of x. So I'm just going to write that as first f of x times g of x all primed. And then from the product rule, I know that that is f primed of x times g of x plus f of x times g primed of x. And this is the product rule. So if I wanted u primed of 1, that would be f primed of 1 times g of 1 plus f of 1 times g primed of 1. And the idea is that I can look at the graph to find any of these that I need. F primed of 1, g of 1, f of 1, and g primed of 1. The two derivatives, the f primed of 1 and g primed of 1, if I gave you like an arbitrary graph, could be quite hard, right? But since this graph is piecewise linear, the tangent line at any point here is just going to be the slope of the line at that point. And since these are straight lines, we can calculate their slopes. So one at a time, let's say what these are. Maybe I'll save the derivatives for last. So I'll just say f primed of 1 times g of 1. Can we tell what g of 1 is? Well, here's my y-axis, here's my x-axis, here's x equals 1. Looks to me like g of 1 is just 1. Plus the f of 1, not f primed of 1, but f of 1 is the y value on the pink graph where x is equal to 1. Looks to me like that is 2. And now I need to plug in for my derivatives. I need to know what is f primed of 1, what is g primed of 1. Those are the slopes, right? The slope of g primed of 1 is the slope of this line, or the slope of the tangent line to that graph at x equals 1. But since g here is a straight line, the slope of the tangent there is just the slope of that line. And you can see that this line here, this blue line, has slope -1. Go down 1, over 1, down 1, over 1, down 1, over 1, down 1, over 1. So g primed of 1 is -1. So over here I'll have 2 times -1. Over here I have this 1 still. And f primed of 1, that would be the slope of the tangent line to the pink graph at x equals 1. So the slope of the tangent line right here where I'm holding my mouse. Since this is also a straight line, the tangent line is that line. So we just need to find the slope of that line. And the easiest spots I see to check here from the origin, if I go over 1, 2, and up 1, 2, 3, 4, looks like that line has slope 4/2 or 2. So this derivative is 2. So I have 2 times 1 plus 2 times -1. That's 2 minus 2 or 0. This is one of the better problems in the homework set, so I don't want to spoil the whole thing for you. Rather than showing you the full solution for the second part, let me just show you how I would begin. I'll give you the first couple steps, and then I'll let you fill in the rest. Are there any questions first about how we got this? Our final answer for that first part then would be u primed of 1 is 0. And we differentiate symbolically. That gets us to here. Then we're told we want u primed of 1, so we plug in 1 for x everywhere. Again, just symbolically, no place where I can actually do an evaluation. And then all of the quantities that I need, I can get out of the graph. And you just have to think a little bit carefully about what each of these things represents. F primed of 1, that's the slope of the graph of f when x is equal to 1, that was 2. G of 1, that's the y value on the graph of g, where x is equal to 1, that was 1. For the second part, to get v primed of 5, I would first symbolically cook up v primed of x, which is the derivative of f of x over g of x. And by the quotient rule, this would be g of x times f primed of x minus f of x times g primed of x all over g of x squared. This is by the quotient rule. So v primed of 5 would be what you get when you plug 5 into this apparatus. That's g of 5 times f primed of 5 minus f of 5 times g primed of 5 all over g of 5 squared. And this is where I'll stop for the second part, because I would like you guys to sort out the values of g of 5, f prime of 5, f of 5, and g prime of 5 from the graphs, just to make sure that you're comfortable with what I did for you in part A. Okay. Any questions on either of these? Alrighty then. So the name of the game, and I just brought the dog in. You're just saying, hi, Moose Wallace, or are you here to stay? Just visiting. All right. The name of the game from here is derivatives of trig functions. This is another one of those places where there's something that is deeply fundamental underpinning the work that is a little bit of a hass, you know, like the binomial theorem showing up in the proof of the product rule, proof of the power rule. There is a limit that we're going to need in here. So let me just tell you at the start, a preliminary result, which I will prove later and use now, is that the limit as h goes to 0 of the sine of h over h. Let me look at this with you in Desmos. Is 1. Now the scale here is not great. This thing's in the way. Y-axis. Here. Here's sine h over h, or sine x over x, if you like. It's called the sinc function. This is actually a quite famous function, very important in signal processing, kind of like a damped harmonic oscillator, but the damping is much less severe. If you look right at 0, whoop, 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 there it is. There's a hole in the graph here. And of course, there's a hole in the graph here. This thing is undefined when h is 0, right? Because the bottom is 0. But you can tell from the graph that this limit should be 1, right? If I'm walking along the graph, getting closer and closer to 0 from the left or from the right, my y values are getting closer and closer to 1. There's just a little hole right there at 1. So this limit is 1. And because logical completeness is somewhat important in this class, I am going to prove that for you. And there are some problems in your homework set that require you to exercise knowledge of this skill. There's another one. And once I get the sine h over h limit, this second limit will be a consequence of that. But again, I'll prove both of these to you. The proof is geometric in nature. It's kind of tricky to follow, and it really derails the whole lecture if I do it in the middle of the argument. So I'm just going to tell you the result now. Go through the derivatives of sine and cosine. And then at the end, I will convince you that these things are true beyond just showing your Desmos graph. The Desmos graph is probably pretty convincing for most of us, definitely pretty convincing to me, but the geometry proof is like a classic part of Calc 1, so I'm going to show it to you. All right, with that out of the way, let f of x be sine x. and calculate f prime of x. I cannot apply the power rule or the product rule or the quotient rule or anything about e to the x because I don't have any of those things. I have a trig function here. So the only thing I could do is write down the limit definition. The derivative of the sine function is by definition the limit as h goes to 0 of f of x plus h minus f of x all over h. And if I plug in the sine function for f, this is the sine of x plus h minus the sine of x all over h. And here's where I get to test the quality of your trigonometry class. What is the sine of x plus h?
Sine x plus cosine and sine x times cosine h plus sine h times cosine x.
I think that sounded correct. So this is sine x cos h plus sine h cos x. This is the sum formula for the sine function. It's one of your trig identities. We're going to use the one for cosine later, but one thing at a time. So I take that identity from your trig class and I use it to expand the first part here. The result, thanks to Robbie, is the limit as h goes to 0 sine x cos h plus sine h cos x. And then I still have my minus sine x. And everything is still divided by h. Well, what we do from here is group terms together. So I have a sine x cos h here. I don't have any other cosines of h, but I do have another sine of x over here. So I'm going to group those terms together. And then this middle guy, I'm going to group as a single thing. So what I'll do is I'll write the middle term first. So that's sine h cos x. And then the other terms here, plus sine x cos h minus sine x. That's my numerator. And rather than writing those all over a single big fraction, I'm going to give each their own denominator here. Each is over h. That is totally kosher, of course. You can always split up a fraction over its denominator. And the limit is being applied to everything. Next, by my limit laws, I can take the limit of this and the limit of this separately. So let's give the limit to each one on their own. I'm also going to do a bit of algebra. So here I've got sine h over h and then cos x. The limit here just involves the variable h. So I'm going to write that as sine h over h times cosine of x. That's fine because cos x is cos x over 1. And if you multiply those fractions across, it's the same. The second piece will get its own limit, lim h to 0. And I'm going to do the same sort of thing. Again, the limit is in h. So the sine of x term here, I'm going to factor that out from the top. And I'll be left with cos h minus 1. Got that sine of x term out here. And this is where those two special limits come in. The limit as h goes to 0 of sine h over h, I have shown and maybe convinced you is 1. The limit as h goes to 0 of cos h minus 1 over h, I have claimed is 0. So this is 1 times cos x plus this is 0 times the sine of x. And 1 times cos x plus 0 times the sine of x is the cosine of x. In other words, the derivative of the sine function is cosine. And that's the whole argument, minus the arguments about special limits. So that is ddx of sine x is cos x. Or if you want, you can write it in primes. Sine of x primed is cosine of x. And if you look at the graphs of those two functions, it's actually pretty obvious. I buried the lead here by not showing you the graphs of sine and cosine together. But this is the part I need you to really remember from the first thing that we've done here today. Derivative of sine is cosine. Let me go ahead and show you those graphs, though. Let me go ahead and show you those graphs in Desmos. I'll give you just a minute. Okay, Desmos coming in. And let me change the scales back to, sorry, I muted myself. Let me change those scales back to something a little more reasonable. Yeah, something like this, right? Okay, so if you're watching the graph of the sine function, that's the red function, and you're trying to figure out its derivative, well, the derivative should be positive here because sine is like going uphill. The tangent lines are positive. The derivative should be 0 right here because that's where I have a horizontal tangent line. The derivative should be negative over here and 0 here again. Well, shit, that's cosine, right? The place where sine has a horizontal tangent, cosine has an x-intercept. Remember the relationships between the original horizontal tangents and the derivative x-intercepts that we talked about last week? This is that. Right, these functions match up perfectly in that sense. Everywhere that the red function has a horizontal tangent, the blue function has an x-intercept. Everywhere the red function is going uphill, the blue function is positive. And everywhere the red function is going downhill, the blue function is negative. So the blue is the derivative of the red. In other words, cosine is the derivative of sine. This is one of the many reasons why your math teachers love sine and cosine so much. Oh, excuse me, I have a call coming from college. Hello. Hi, Beverly. I'm doing pretty good. What can I do for you? I don't know why HR thinks I'm free to talk right now about health insurance, but I'm not. So yeah, no. Derivative of sine is cosine, right? Or sine primed is cosine. That's the result. The argument for cosine is very similar. I am going to run through it, but I will be a little bit hastier with the algebra. I will let f of x be cosine of x and find f primed. Same stuff, f primed of x. I'm going to jump straight to it. Is the limit as h goes to 0, cos of x plus h minus cos of x all over h. Does anybody remember the sum formula for cosine?
Cosine x times cosine h minus cosine h times sine h.
Excellent. So that's the sum identity for cosine, which will allow me to expand this numerator. And the minus cos x is still lingering. And we're going to do the same algebra trick. I have cosine of x now showing up in two different places, here and here. So again, this first term and this last term will be grouped together given their own fraction. This first term, so that middle term, I will pull out separately. So we have lim h to 0. I have negative sine of x times sine of h over h plus cos x cos h minus cos x over h. From each of those, I can get here. I pop the sine x off to the side. Let's pop the negative sine x off to the side. So I'll have sine h over h times negative sine of x. We'll write it like that. Plus lim h to 0. I'll factor the cos x out here. And what's left is cos h minus 1 over h times cos of x. And again, the sine h over h limit, as h goes to 0, this piece becomes 1. The cos h minus 1 over h limit, as h goes to 0, this piece becomes 0. So we get 1 times negative sine of x plus 0 times the cosine of x, which is negative sine of x. So the derivatives of sine and cosine are very nice, perhaps not as nice as possible, but very, very close. Derivative of sine is cosine. Derivative of cosine is negative sine. You might ask, are there some similar functions where the derivative of sine would be cosine and the derivative of cosine would be sine itself instead of negative sine? Yes, they're called hyperbolic trig functions, and we will talk about them. Sinh and cosh usually is how they're pronounced. But we'll get there when we get there. For now, we get the crucial result that d dx of cos x, not quite as nice as negative sine x, still very nice, i.e. the prime notation cos of x all primed, negative sine of x. So those are the two big results for today. Everything else kind of comes as natural consequences of product and quotient rule stuff. But before I can really pretend like we've done this all, we got to prove those limits. The hard work is going to be in the sine h over h limit. And I'm going to rewrite it in terms of the variable theta because it's going to be understood through a geometry argument. The argument I linked to you on Stack Exchange at the end of our last class, in fact, is the exact one that I will use here. It employs some inequalities, which come from geometry, and then some squeeze theorem. So let's do it. People always like to ask, are you responsible for these proofs? No, you're not responsible for this proof or the derivative proofs we just went through, right? Just like you're not responsible for the proof of the power rule. It's just something I have to show you, otherwise I'm being a bad math teacher, because math should be 100% logical and internally consistent. So we're going to prove this. I want to show I'm just going to swap the variable to theta because it'll make it a little bit easier to understand what's going on geometrically, because we usually think of angles as being measured by Greek letters. So we'll show that this limit is 1. But of course, lim theta to 0 sine theta over theta is the same as lim h to 0 sine h over h. It's just a matter of the labels. And we're going to do this geometrically. Here's the unit circle. Here's the angle theta. That means that this point right here on the unit circle, right, is cosine theta comma sine theta. In particular, this height right here is sine theta. If I extend that ray out to meet this, then this point right here, remember, is 1 comma 0. This point right here, I'll label it as cos theta comma sine theta. So this side length right here is 1. The angle inside is theta. And the big triangle is similar to the little triangle. They have the same angles. They are both right triangles, where one of the internal angles is theta. So the ratio of side lengths, sine over cosine, must be the same as this length over 1. So the argument begins like this. The big triangle is similar to the little triangle, which tells us that this length over this length, we call this, I don't know what to call it. I don't want to use H. Call this just B. Tells me that B over 1 is equal to this height over this length. Now this point here is a point on the unit circle, so its x coordinate is cos theta, so this x distance is cos theta, and this y distance is sine theta. So B over 1, the total length of the big triangle, down here, the base of the big triangle is 1. B over 1 must be equal to sine theta over cos theta. That's similar triangles have the same ratio of side lengths. In other words, this is tangent theta. So B here, this side length, is tangent theta. Next, what I'm going to do is compare 3 different areas. One of the areas I will shade green here. The area of the sector of that circle. And if you take the area of the sector of a circle of radius r, that area, when theta is 2 pi, you get the whole circle. You know, that's pi r squared. If theta were pi, it would be half the circle, which is 1/2 r squared. In general, this is 1/2 theta r squared. That's the formula for the area of a sector of a circle. And the easiest way to convince yourself of that is to realize that it needs to be a linear function of theta. Right? When theta is 0, the area should be 0. When theta is 2 pi, the area should be pi r squared. Well, the only way to get pi r squared out of this when theta is 2 pi, imagine plugging in 2 pi for theta, the 1/2 cancels the 2, is if the formula is 1/2 pi r, 1/2 theta r squared. So that green area here, we're on the unit circle, so the radius is 1. So the green area is 1/2 theta times 1 squared, or just 1/2 theta. The other 2 areas in play here are the area of the little triangle and the area of the big triangle. The area of the little triangle, I will crosshash shade in purple. And in order to avoid cluttering the shit out of this picture, I'm not going to shade the big triangles area. But these are the things we are going to compare. Okay. The purple triangle area as with all triangles, is 1/2 base times height. And the base of that purple triangle is cosine theta. The height of that purple triangle is sine theta. So that area is 1/2 cos theta sine theta. And the area of the big triangle this side length is 1, the base. This side length we argued earlier is tangent theta. So his area is 1/2 times 1 times tangent theta, or just 1/2 tangent theta. The nice thing about these shapes is that one fits inside the next, fits inside the next. The purple fits inside the green, and the green fits inside the big triangle. Which means that of these three, the purple must be the smallest. The way this is described is by inclusion. Right, one being included in the other. By inclusion, the green area is less than or equal to the purple area. Oh shit, no, I fucked up. I'm so sorry. I already fucked up. By inclusion, right, the smallest one is the purple one. He fits inside the green. And then both of those fit inside the big guy. So purple, sorry, by inclusion, the purple area is less than or equal to the green area, which is less than or equal to the unshaded area, the area of the big triangle. So of these three shapes, the purple triangle is the smallest. He fits inside the green sector. So next biggest is the sector. Both of those, one inside the other, fit inside the big triangle. So the big triangle is the biggest. So what is this? This is 1/2 cos theta sine theta. Is less than or equal to 1/2 theta is less than or equal to 1/2 tan theta. So by inclusion, I have this relationship between the areas. Multiply through everywhere by 2. I'm going to stop the color coding now because it's troublesome to switch pens. We got cos theta sine theta is less than or equal to theta itself, which is less than or equal to the tangent of theta. Divide through everywhere by sine theta. And you get cos theta is less than or equal to theta over sine theta is less than or equal to, if you take tangent theta and divide it by sine theta, that's sine over cosine, divided by sine, you get 1 over cosine or secant theta. Now take reciprocals everywhere. I'll write it all in terms of sine and cosine. On the left-hand side, you get 1 over cos theta. Taking the reciprocal flips the inequality around. The middle is sine theta over theta. The reciprocal of secant is cos theta. Now apply the squeeze theorem. The limit as theta goes to 0 of 1 over cos theta. Cos theta is, it doesn't have any problems at 0. 1 over cosine of 0, that's fine. Cosine of 0 is 1. This is 1 over 1 or 1. And the limit as theta goes to 0 of cos theta itself is cos of 0, which is also 1. So by the squeeze theorem, the guy in the middle must also go to 0, or sorry, must also go to 1 as theta goes to 0. And that's the proof. It's a little bit of work. It's a little bit of work. There are reasons why calculus took a while. All right, there's a reason why you don't have like Rene Descartes whipping out calculus. There's a reason why Euclid was not rocking calculus, because this shit a little complicated, man. This is something I'm showing you for your enrichment. I will not test you on the argument made here. The shapes, inclusion, cooking up and manipulating this inequality. It's a little bit more than I would expect you guys to do on your own. But the end result, sine theta over theta going to 1 as theta goes to 0, you do need to remember that. I will ask you questions about it. And the next thing I want to do is just show you an example of a problem you can cook up using this limit, namely the other limit that we needed. And then I'll do one more, and then we'll get secant, tangent, cosecant, cotangent derivatives. All right, if you want it, it's here. You can take a screen cap if you like. The hard work is coming up with the geometry, obviously. So here, if you want to cap it, this is the hard work.
Could you move it up just a little bit, please?
Sure.
Thanks.
It is important to remember that this side length being tangent theta comes from similar triangles, or however you want to get it, but we do need that. But yeah, here's the work besides that. All right. Are there any questions you guys would like to ask about this? Fun use of the squeeze theorem, right? This is, truth be told, this is why we teach the squeeze theorem, right? So I can show you the derivative of sine and cosine in a way that does not involve circular logic. Not that the squeeze theorem doesn't have other utility, but this is the main reason. Okay. So other limits we can get. From lim, I'll write it as lim x to 0 sine x over x equals 1, right? Again, the variable doesn't matter. You can use h's, x's, thetas, whatever you want, and you will see all of them. How about this one? I claimed earlier that this was 0, but I never proved it. And I promised no more crazy geometry arguments. If I want to do this, the trick is to force or induce a trig identity to let me kind of lean on this. So if I want to change some cosine stuff to some sine stuff, what I'd really like to do is make cosine squared show up somewhere. And I can do that by multiplying by the conjugate. Cos x plus 1 over cos x plus 1. Distributing. I get lim h to 0, FOIL the top. Oh, I wrote x's and h's, didn't I? Son of a bitch. H. Multiply by cos h plus 1 over cos h plus 1. I'm sorry. So distributing, I get cos squared of h plus cos h from my outers minus cos h from my inners goes away. Minus 1 from my lasts over h times cos h plus 1. Now, we know sine squared h plus cos squared h is 1. This is the first Pythagorean identity. And this implies, if I, let's see, subtract the 1 over here and subtract the sine over here, then you get cos squared of h minus 1 equals negative sine squared of h. So that cos squared minus 1 upstairs is negative sine squared of h. And then downstairs I have h times cos h plus 1. Now I'm getting to a place where I've got sines of h upstairs and I've got an h downstairs. I'll be able to make use of this. Everything else is pretty well behaved. I can pop the negative out. I get negative lim h to 0, and then I split up this fraction as sine h over h times sine h over cos h plus 1. Again, our limit laws allow us to take the limit of each of these pieces separately. So I'll write it negative lim h to 0 sine h over h times lim h to 0 sine h over cos h plus 1. That first piece is 1 by our geometry argument. So I have negative 1 times. This piece is continuous at 0, right? Cos h is 1, sine h is 0, so this is 0 over 2. So you get negative 1 times 0, which is 0. So yeah, cos h minus 1 over h really does go to 0. But this is far from the only thing we can get. right? There's actually a whole bunch of other important limits we can get, and some of them show up in your homework. I would like to show you one example of a problem like that, so you're ready for the technique that's required, and then we'll get back to differentiating trig functions.
How did you get 0/2 again?
I'm sorry?
How did you get 0/2?
I just plugged 0 in here. So the sine of 0 is 0, and the cosine of 0 is 1. So I've got 0/1 + 1, which is the 0/2. Yeah, the neat trick is by kind of stealing the h from the downstairs and putting it with the sine h upstairs. This piece I now know goes to 1, and he was the thing that made this hard. Okay, I know we're moving a little bit quick, but I do want to keep us on schedule. I feel bad I've been holding you guys late after class. So let's look at the limit as x goes to 0 of sine 3x over 5x. There are several problems in your homework that kind of have a similar feel to this. Let me point them out. The trick is going to be to make a little substitution. So I'm going to replace 3x by h at some point here and rewrite this as a limit h goes to 0. We need to figure out how the 5x is going to fit into all of that. The homework questions that are relevant here are like these last 38, 39, 40. These all use the same sort of trick, right? So the one I'm doing right now is very similar to 38. Sine 3x upstairs is going to stay. Downstairs, I'm going to bring the 5 out. And if I put a 1 up here, this would be a true statement, right? 1/5 times sine 3x over x is the same as sine 3x over 5x. But what I want to do, and what you want to do when you solve these problems, is have sine of something divided by that same thing, right? We've seen whether it's x, h, or theta, I don't give a shit. Sine of something over that same thing will go to 1 as that thing goes to 0. So what I really want down here isn't an x, it's a 3x. And in order to do that, I need to put a 3 out here. So you can see if you canceled these 3's and moved the 5 back in, you would have this. These are equal to each other. It's just a little bit of symbol juggling. And we do that symbol juggling to try and get the same thing in here as we have down here. I cannot change what's in here. I have very little control over what's going on inside the sine function, because the sine function is like an impenetrable algebra box. There's no amount of algebra that will let you break into the sine function. But this shit downstairs is just 5x. I can do whatever the hell I want with that. So I pop the 5 out, I replace it by a 3. And I can do that as long as I bring a 3 up here. You can think of it like I'm multiplying by 3/3. The 3 upstairs stays out, the 3 downstairs comes in, and the 5 downstairs comes out. And we're going to substitute, I'll call it theta equals 3x. So everywhere there's a variable here, it's now attached to the number 3. And observe that theta goes to 0 as x goes to 0. If theta is 3x, then when x goes to 0, theta goes to 0 as well, right? 3 times 0 is 0. So I can now rewrite this limit as lim theta goes to 0, sine of theta over theta times 3/5. And this limit is the one we did all that work for. This limit is 1. So you get 1 times 3/5, and on a good day, that is just 3/5. And if you feel like you see a pattern or a relationship between this thing and the answer, you're 100% right. If you see a pattern between the shape and numbers here and the shape and numbers in the answer, you are 100% right. It is what you think it is, and it is that shit every time. But you need to know how to show it. You need to be able to demonstrate the steps that get us there. So as you practice those problems, there's several of them in the homework. Mimic what I'm doing here. You will be just fine.
Would it be the same answer if instead of sine, it was cosine or tangent, or one or the other?
One of those, yes. The other one, no.
Probably not tangent, right? It's the other way? Okay.
So that you can swap sines with tangents here without consequence, because tangent is sine over cosine, and cosine of 0 is 1. All right, so one of the other homework problems has you doing precisely that, right? If given lim x to 0, tangent of ax over bx, use tan theta equals sine theta over cos theta. So I can rewrite that as lim x to 0 sine ax over cos ax, all divided by bx. And then a little bit of algebra later, you should arrive at something like sine ax over bx times 1 over cosine of ax. And since the cosine term is well behaved near 0, cosine of 0 is not 0, it's 1. This piece actually doesn't mess things up at all. You end up with this, which is what we started with here, right? Same sort of thing. One of your other problems has like a sine of ax over a tangent of bx, something like that. Rewrite the tangent as sines and cosines and try to massage it into this form, sine theta over theta stuff. So what works for sine works for tangent, but does not work for cosine. Okay. I promised derivatives of all 6 trig functions. So let's do it. So far, we have that the derivative of sine x is cos x, and the derivative of cos x is negative sine x. The other 4 trig functions are built up as ratios of sine and cosine, right? Tangent is sine over cosine, cosecant is 1 over sine. So to get the derivatives of the other trig functions, you just need to combine these 2 facts with the product and quotient rules. I will work for you tangent and secant. I will let you sort out cotangent and cosecant. The derivative of tangent is the derivative of sine x over cos x, because tangent is sine x over cos x. Which by the quotient rule, I'm going to write this out in the prime notation, is low d high cos x times the derivative of sine x, so sine x primed, minus high d low, that's sine x times the derivative of cos x, all divided by the square of the bottom. And you see a theme every time I use the quotient rule, I write it out with the primes. You should do that too. The derivative of sine is cosine, so this is cosine times cosine, or cos squared. The derivative of cosine is negative sine, so this is minus sine x times negative sine x is plus sine squared x. And then downstairs is cos squared x, right? Cosine of x all squared is cos squared x. The numerator you immediately recognize as 1. First Pythagorean identity. So the derivative of the tangent function is 1 over cosine squared. Nobody would say that though. We call 1 over cosine the secant function. So that is secant squared x. The derivative of tangent is secant squared. This is one of the facts of life. Mommy and daddy left them out with the birds and the bees, but damn it, they should not have. Right up there with e to the x being its own derivative. The last thing I'm going to do for you today is differentiate the secant function. ddx of secant x is ddx of 1 over cosine x, because secant is by definition 1 over cosine. And again, a quick application of the quotient rule, you have low d high, so cos x times the derivative of the top, which is just 1, minus the top times the derivative of the bottom. So cos x times 1 primed minus 1 times cos x primed, all over cos x all squared, or cos squared of x. This one takes a little bit more love, but just a little bit. The derivative of 1 is 0, so you've got cos x times 0 minus 1 times the derivative of cos x. Well, the derivative of cosine is negative sine, so that's minus negative makes plus sine of x all over cos squared x. Of course, cosine x times 0 is 0, so you get sine x over cos squared x. And like the last one, nobody would leave it like this. That is the same as 1 over cos x times sine x over cos x, or secant x tangent x. And that's the end of the show for him. All right, I want to just write down in summary the derivatives of all 6 trig functions. The remaining 2, cosecant and cotangent, I will not prove for you here. I will tell you though, that is a common question on my first test. All right, prove the derivative of cosecant is negative cosecant cotangent. The arguments go the exact same way as the derivative for secant here, just with the functions replaced by their co-functions. right? I do see we still have some folks writing. I don't want to rush it. If you have to go, I understand. I will take just 10 seconds more for those who can stay to summarize the results, but nothing new. Here we go. In summary, the derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of tangent is secant squared. The derivative of secant is secant tangent. These four we proved. The remaining two follow very similar rules. The derivative of secant is secant tangent. The derivative of cosecant is almost cosecant cotangent, but with a negative. And similar to how the derivative of tangent is secant squared, the derivative of cotangent is almost cosecant squared. Just add a negative. So there are patterns here. You need to know these like water. They should just flow off your tongue. You don't even have to think about it. If you use them enough, that will happen. At least that's the case for me. If you are not the sort of person where things just bake in automatically from using them in the context of a problem, you may want to consider some flashcards. The very last thing I'll say here, it's easy to get lazy about writing the variable, right? When I say this, I say the derivative of tangent is secant squared, and that's fine. But when you write it, you need to say the derivative of tangent x is secant squared x. Do not get sloppy with the variables. If you write a trig function without a variable or number inside of it, it has zero meaning, and I can give zero credit. So please, every time you write a trig function, write the variable inside. I don't know why, but this is the point where people start getting sloppy with that shit. Don't be that person. I don't want to take those points from you. So please, remember the derivatives of the 6 trig functions here. Remember, when you write them down, you need to write the variables inside. The next thing we're going to learn to do is differentiate composite functions. That's where you plug one function into another. There's a special rule for that called the chain rule. Once we have that, you will have all the differentiation rules you need to differentiate just about anything. That's it from me for today, gang. I know it was a busy day.
Can I ask a quick question?
Sure. Yeah. So I'm done here. If you gotta go, you gotta go. Yeah.
Okay. I was just wondering, you were saying earlier that something's going to show up on the first test. What was that again?
2 things that often show up on my first test. One, proof of one of these. Right, so mimicking the arguments I used for secant and tangent, find the derivative of cosecant, you'd write it as 1 over sine and then apply the quotient rule, or find the derivative of cotangent, you'd write cotangent as cosine over sine and apply the quotient rule. That is a very common problem on my exam 1. Another very common problem on my exam 1 is something that makes use of the sine x over x limit, right? Like the sine 3x over 5x as x goes to 0. That sort of stuff shows up frequently.
All right, thank you.
Mm-hmm.
You had also mentioned last week that you were going to, did you schedule the test yet?
Oh yeah, good question. So no, I have not just yet. So once we finish the chain rule, do I resolve this up? The usual way I do this is after we cover the last section that will be on the test, which for us here is the chain rule, then I release the study guide. So next week we will learn the chain rule, and I will drop the study guide for the test on that day. Next Monday is when we'll introduce the chain rule. We'll probably spend Monday and Wednesday on the chain rule itself, then review for the exam on Friday, and then the exam will be the following Monday. So I reserve the right to move that around just a little bit, But looking at the calendar as it is now, I would guess that your first exam will be on the 30, no, sorry, what did I say? 31st, we're gonna do the chain rule, more chain rule, review the 7th. Most likely date for exam 1 is February 7th.
Thank you.
Thank you for having study guides.
Yeah, no problem. No
Yeah.
problem. Now remember the rule for the study guides, the way these work, you gotta, they'll be released on WebAssign, but you need to write out the solutions to your problems. You need to write it all out, scan it, and submit it in Canvas in order to get the grade. That's how they're graded. I don't care if you answer the questions in WebAssign. We can all put shit in the math way. What I want to see is your work. And I want to be able to look at your work and make comments on it and give you feedback before the test. So I'll release the study guide a week before the test. Get it submitted on Canvas as soon as you can so I can mark it up and you can get some useful feedback before the test itself. Alrighty, the study guide, by the way, graded just for completeness, right? So there's absolutely no reason to copy stuff out of Symbolab or Mathway or Wolfram or Bartleby or Chegg or any other fucking place. Just show me what you do. That way I can give you the sort of feedback that you need for the test. If you have an answer, just something written for each problem, you're going to get full credit on the study guide. So just show me whatever you know to do, however you would approach it if you're on a desert island, and I will give you the sort of feedback that'll help you prepare for the exam.
Also, whenever you get a chance, could you approve some extensions afterwards?
Yes, let me take a look at that. I haven't done that yet today. So if you've got extension requests in or you need to get one in, go ahead and drop it in the next 5 minutes or so, and I'll clear those out in the next 30.
All right, I appreciate it.
Of course. Anything else before we wrap up here, guys?
Thank you, John.
All right, I hope everybody has a good, safe weekend. Wrap up that homework, and I'll see you on Monday for the chain rule.